Good morning. Let me know if I'm audible. Yes, good morning. I'm audible? Yes. Thank you. Chaliye, let us start the subject then. Yesterday we have discussed the concept of applications of Bernoulli equation. Today we are going to start the last topic of this chapter, and the topic is regarding the concept of vortex motion. Let me write date first of all. Today is 7th of 10th, 2020. Today we are going to start the concept of vortex motion. Vortex motion. Now, what do we exactly mean by vortex motion, first of all? Let us describe vortex motion and then we'll go into details. Vortex motion is basically flow of a fluid body about a particular axis. Let us say there's a particular axis about which the entire fluid body is going under rotation. Okay. This is not rotational flow. This is flow about a particular axis. Please understand. Rotational flow basically means that a fluid particle is rotating about its own axis, whereas vortex motion means the entire fluid body is rotating about a particular axis. Okay, these are two different things. So let me define over here vortex motion. Definition. Motion of a fluid body about a particular axis. Particular axis such that the normal or radial velocity is zero. So basically, if the entire fluid body is rotating, it won't have a radial velocity, it will only have a tangential velocity over here. Such a motion is known as your vortex motion. Okay. Now, regarding this vortex motion, there are multiple types of vortex motion, but our examinations are going to deal only with two types of vortex motion. One is known as free vortex motion, the other is known as forced vortex motion. So we are having vortex motion, vortex motion can be classified into two types. So according to our subject, vortex motion can be classified into two types. Which two types? The first one is known as free vortex motion. First one is free vortex motion. Second one is forced vortex motion. Forced vortex motion. Okay. Apart from this, there are many more types, but we are not concerned with all those types. Our examination is going to deal only with these two types. Let us now start with the concept of free vortex motion. Let us start with the first one, which is known as free vortex motion. Free vortex motion. Now, regarding this free vortex motion, how do we define this free vortex motion first of all? Free vortex motion is defined as vortex motion. When I write VM, think it is vortex motion. Vortex motion in which the net external torque is equal to zero. the vortex motion in which the net external torque acting on the fluid body is equal to 0 is known as your free vortex motion. Now you see, when external torque becomes equal to 0, that time the value of velocity times r becomes equal to 0. Velocity times r becomes equal to 0. Why is it so? The reason is torque is basically equal to d by dt of mvr. mvr over here stands for angular momentum. Okay, so torque is equal to rate of change of angular momentum. If the net external torque is 0, that means mvr is constant. Mass of a fluid body is already a constant. That means v times r also becomes constant. If v times r becomes constant, from here we have a very important result. Very important result. Remember this thing, that in the case of free vortex motion, velocity has to be inversely proportional to radius. This is a very important result. In the case of free vortex motion, velocity has to be inversely proportional to radius. This result is very important for us. What do I mean by this thing? The meaning of this thing is, imagine that you are having a particular axis. You are having a particular axis. Okay. And you are having some fluid body which is rotating about this particular axis. About this particular axis, some fluid body is rotating. Now, if I take two particles, let us say I take a particular particle at some distance r1. I'm choosing a fluid element over here. There is some fluid element over here. This fluid element, let us say, is having some tangential velocity. That velocity is equal to v1. Okay, about this axis there is rotation, or the fluid body is rotating, and at a distance of r1 from the center, I am having a fluid particle or fluid body. Let us say its velocity tangential is v1. The value of this v1 has to be inversely proportional to r1. Imagine I take another fluid particle. Imagine I take, one second. Imagine I take another fluid particle. Let us say this fluid particle over here is at some distance r2. We are having some other fluid particle. Let us say this is having certain velocity tangential that is equal to v2. Now, what relationship can I write between these two? Since velocity is inversely proportional to r, I can write v1 upon v2 is equal to how much? It should be equal to r2 upon r1. v1 upon v2 is equal to r2 upon r1. That means as you go farther from the center, this is central axis. As you keep going farther from the center, the velocity keeps on reducing. Velocity keeps on reducing. This is regarding the concept of free vortex motion. Apart from this, you also have to remember some more points regarding free vortex motion. And that is, in the case of free vortex motion, the flow is supposed to be rotational. So second point under free vortex motion only, free vortex motion observes rotational flow. Free vortex motion observes rotational flow. Should do one thing, you can take a snapshot of the previous slide. Take a snapshot quickly of this particular slide. This is the first slide for today's class. So I was discussing regarding one second please. I was discussing regarding free vortex motion. It's not rotational, I'm sorry. One second. This is free vortex motion observes irrotational flow. Irrotational flow. Please be careful. Free vortex motion observes irrotational flow. The last point regarding free vortex motion, 3 points you have to remember. First point was velocity is inversely proportional to r. Second point, free vortex motion observes irrotational flow. Third point. Now you see, since free vortex motion is observing irrotational flow, I can take any 2 points in the flow which may or may not lie on the same streamline, and still I can apply Bernoulli equation. Because remember, in the case of irrotational flow, Bernoulli equation is valid across any 2 points, whether they are lying on same streamline or they are not lying on same streamline. That means I can write over here, Bernoulli equation is valid across any 2 points. That means, let us say this particle 1 or point 1 and point 2, both of them may be or may not be lying on same streamline. Let us say they may be or may not be lying on same streamline, but still I can apply Bernoulli equation between these 2 points. So now I can say P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. This is what I can write in the case of which vortex motion? Free vortex motion. So 3 points you have to remember regarding free vortex motion. In your short notes, whenever you write your short notes, you're going to mention these 3 points. First point, velocity is inversely proportional to r. Second point, flow is irrotational. Now, third point is a result of irrotational flow. According to irrotational flow, between any 2 random points, whether they lie on same streamline or they do not lie on same streamline, you can apply Bernoulli equation. So any 2 random points you take, you write Bernoulli equation, you say P1 by gamma plus V1 square by 2G plus Z1 equal to P2 by gamma plus V2 square 2G plus Z2. Likewise, you can write down. Okay. This is regarding the concept of free vortex motion. How the flow is irrotational, you can prove it after some time. I'll give you a particular equation. From that equation, you can prove the flow is irrotational. Moving further. The next kind of vortex motion we are having is known as forced vortex motion. This is more important for you. Forced vortex motion. Forced vortex motion. This is more important. Now you see, you're going to get some results which are exactly opposite to what we got in the case of free vortex motion. Some results which are exactly opposite to the results in free vortex motion. Now in forced vortex motion, first thing, you're going to have a constant external torque, external torque on the fluid body, This is the first thing. Previously, what was happening? You are having a zero external torque. If you see, in the case of free vortex motion, we have mentioned that a vortex motion in which the net external torque is equal to 0. Whereas in the case of forced vortex motion, you are going to have a non-zero constant external torque acting. You see, by the virtue of this constant external torque, what is going to happen is every fluid particle has same angular velocity. So in the case of forced vortex motion, every fluid particle is going to have same angular velocity. If it is having same angular velocity, I can say the value of omega has now become equal to constant. The value of omega is now become equal to constant, which implies omega is basically V upon R has become equal to constant. It has become equal to constant, which implies velocity is directly proportional to R. So in the case of forced vortex motion, velocity is directly proportional to R. This again is very important. Velocity is directly proportional to R. That means if I take any 2 points in forced vortex motion, I can say V1 by V2 has to be equal to corresponding R1 by corresponding R2. So velocity over here, as you keep going away from the center, velocity is linearly increasing. Previously, you remember, it was inverse proportionality. Velocity was inversely proportional to R. So as you keep going away, velocity was keeping on decreasing. Over here, as you keep going away, velocity is keeping on increasing. This is the first point. Apart from this first point, two more points you have to remember in the case of forced vortex motion. What is the second point you have to remember? The second point. Now look over here. Free vortex motion was observing irrotational flow. Forced vortex motion observes rotational flow. Over here you are going to have rotational flow. Forced vortex motion is having rotational flow. Now recall, in the case of rotational flow, Bernoulli equation is valid only across 2 points lying on same streamline. So imagine this point 1 and point 2 are on same streamline, then you can write Bernoulli equation for that. But in general, if you write Bernoulli equation, that becomes invalid. So let me write over here. Bernoulli equation is valid for points belonging to same streamline. Bernoulli equation is valid for points belonging to same streamline. In general, imagine I'm having 2 points, point 1 and point 2. What can I write for these 2 points? Please observe this thing. This might be new to you. Okay. And this will look slightly strange also. But remember this thing. In general, in the case of forced vortex motion, if you're having 2 points, you can then write P1 by gamma minus V1 square by 2G plus Z1 has to be equal to P2 by gamma minus V2 square by 2G plus Z2. Please be careful with this thing. If you are having forced vortex motion, in general, what you can write is P1 by gamma minus V1 square by 2G plus Z1 has to be equal to P2 by gamma minus V2 square 2G plus Z2. You can take a snapshot of this particular slide. This is regarding the concept of forced vortex motion. I'll give you examples, don't worry. Those are not taken the snapshot of the previous slide, you can take down. This is the first slide for today's class. Over here, we defined what is vortex motion. Then we said there is a classification over here. One is free vortex, the other is forced vortex. Okay. Then over here, we have discussed the differences between free vortex and forced vortex motion. Okay, many of you are having many doubts regarding why minus is coming over here. Okay, why are we applying some minus sign over here? The doubt is natural only. The reason actually for all these equations coming, everything coming, is the next topic, what I'm going to discuss, which is known as the equation of pressure in vortex motion. Please be patient for some time, you'll understand everything. Right now, what I want you to remember is 3 things. First thing, for free vortex and forced vortex, how is velocity varying with respect to radius? That is the first thing. Second thing, free vortex motion irrotational, forced vortex motion rotational. Third thing, Since free vortex motion is irrotational, any 2 points you take, you apply Bernoulli equation. But in forced vortex motion, you can apply P1 by gamma plus V1 square by 2G plus Z1 equal to P2 by gamma plus V2 square by 2G plus Z2. But you can apply that only if both point 1 and point 2 are lying on same streamline. In general, if they lie or did not lie on same streamline, there is one equation which is always valid in forced vortex motion. That equation is this equation I have shown over here with a negative sign. Why all these things are coming, you're going to see now. Okay. Regarding the application of torque or the example, I'll be taking problems where you'll be seeing the examples. Okay. I'll be taking some problems. I'll try to take 2 problems. Both of them will be slightly difficult problems. That time you'll be understanding how free vortex motion takes place, how forced vortex motion takes place. Okay. Now, after having understood all these things, let us move further. There is one more type of vortex motion. That vortex motion is going to have a combination of free vortex and forced vortex. A combination of free vortex and forced vortex is going to be there. That kind of vortex motion is called as Rankine vortex motion. So there is something called as Rankine vortex motion. Rankine vortex motion. So how do we define this Rankine vortex motion? We can say Rankine vortex motion is a vortex motion in which a combination of free vortex and forced vortex takes place. A vortex motion in which a combination of free vortex and forced vortex takes place, that is called as Rankine vortex motion. Okay, let me take an example of Rankine vortex motion. This is an example question. Example with the question itself. Very good question. The question says, imagine you are having a container. You are having quite a big container. Excuse me. You are having a big container over here. Okay. Let us say this container is open. Cylindrical kind of container having a radius capital R, very big radius capital R, let us say. Okay. Now I'm choosing a centroidal axis of this particular container. Imagine I have chosen a centroidal axis. Let us say this is a centroidal axis of this container. This is a centroidal axis of this container. Suppose there is some fluid filled in over here. Suppose there is some fluid filled in over here. Now what I'm doing is, about the central axis, suppose I'm having a paddle wheel. I hope you understand a paddle wheel. There is a paddle wheel, let us say. This paddle wheel, I'm applying some torque over here so that the value of omega in this particular region is remaining constant. So imagine there is a paddle wheel. Paddle wheel, you can imagine, those who don't understand paddle wheel, you can imagine something which is used for making buttermilk. Okay, you have that kind of churner for making buttermilk, right? Something like that, let's say. You're using that thing in order to maintain a constant value of omega. This is how we actually apply torque. Okay, you either spin this cylinder or you spin a particular paddle wheel so that to apply you're applying a torque on this particular fluid. Let us say you are applying some torque over here so that omega in this entire region remains constant. Which entire region am I talking about? I'm talking about omega in this particular region. omega in this particular region is remaining constant. Till where paddle wheel is there, till there omega is remaining constant. Let us say this radius over here is equal to some radius r1. This radius over here is equal to some radius r1, and this radius over here is some radius r2. It is equal to some radius r2. Let us say r2 is very, very big. The value of r2 is extremely high. Okay. So this is what I'm having right now. Now, if you see within this centroidal region, that is R1 region, I'm going to have what kind of vortex motion? If you observe, this particular vortex motion is experiencing an external torque such that the value of omega is remaining constant. This kind of vortex motion is forced vortex motion. Forced vortex motion. Now, coming to this particular thing, you're not having any external torque acting by any external source on this fluid body, but this fluid body also is going to experience some vortex motion. This kind of vortex motion is free vortex motion. Now you see in this entire container, the vortex motion you're having is a combination of forced vortex motion and free vortex motion. A combination is there. The question asked over here is, you are supposed to draw the diagram or the variation of velocity with radius for this particular case. So let us say the question over here is, draw the graph of velocity versus radius. Draw the graph of velocity versus radius. Let us see how the graph of velocity versus radius is going to come. Now, first of all, let me take this axis, vertical axis, as the vertical axis I'm having over here is velocity axis. The horizontal axis I'm having over here is radial axis. Okay. Now I have to see how the graph of velocity versus radius is going to appear. First of all, in the region of forced vortex, I know in the region of forced vortex, velocity is supposed to be linearly varying with respect to radius. If velocity varies linearly with respect to radius, I'm supposed to start with 0 over here. I'm supposed to start with 0 over here, linearly move up. I'm going to move up until which radius? Let us say some radius R1 is there. Until that particular radius, I'm supposed to keep on moving up. So let us say the first part for forced vortex motion is, I'm going to start from here. I'm going to have a linear variation. So let us say this is a linear variation I'm having, and it is going to be valid up till what radius? It is going to be valid up till the radius R1, let us say, the radius R1. This is a region of forced vortex motion. After that, from this particular velocity, I'm going to have free vortex motion taking place. And free vortex motion, if you remember, is going to have inverse proportionality. Inverse proportionality basically means you're supposed to have a rectangular hyperbola. You're supposed to have a rectangular hyperbola. That means you'll have something like this, a rectangular hyperbola over here. Okay, so this is the region of forced vortex motion. This is for free vortex motion over here. Okay. Now, if boundary condition of R2 is considered, suddenly the velocity will drop down to 0 because no slip condition might be there. But imagine if R2 is extending towards infinite, you're going to have this hyperbola. It will never meet with this thing, but keeps on decreasing. It keeps on decreasing. So this is the graph for a Rankine vortex motion. Okay. You can take a snapshot of this particular slide. Chaliye. After having taken down till here, the next thing we are having over here, see, you can draw the graph by checking the equation. You will get it this way only. Rectangular hyperbola is supposed to be in this direction. Chaliye. Moving further, first the concept of Rankine vortex motion. Now let us come to the topic which should actually clear your doubts. Most of you are having questions regarding why that negative v square by 2g is coming. Okay. First of all, that entire equation is not Bernoulli equation. When I write P by gamma minus V square by 2G plus Z, that is not Bernoulli equation. That is just an equation which is defining that particular flow. But all those things are coming from a topic known as equation of pressure in vortex motion. This topic over here is equation of pressure in vortex motion. Equation of pressure in vortex motion. Equation of pressure in vortex motion. Now please understand that if you're having a particular fluid body, let us say, suppose there is some fluid body you're having. One moment, please. Imagine this is a fluid body we are having. And about a particular axis, there is some vortex motion developed. Let us say this is central axis. About this particular axis, there is some vortex motion developed. Now this can be free or forced. I'm not worried about that. Let us just say there is some vortex motion about this thing. Okay. When I'm applying torque, it basically means I'm applying torque on the fluid. If I'm not applying torque, it is a free vortex motion. Still, the fluid is having some kind of rotation. Okay. Now, please understand one thing, that the pressure in the case of vortex motion is not going to be only with respect to z-axis. The pressure variation is not only with respect to z-axis. The pressure variation will also be with respect to r-axis. So there are two axes over here important for me. There are two axes important for me. One axis over here is z-axis. The other axis over here is radial axis. Two axes are important. Pressure should vary with respect to r as well as with respect to z. Pressure is supposed to vary with respect to both r and z. That means if I take a fluid element somewhere over here, just imagine I'm taking some fluid element somewhere over here. There is some fluid element, let us say, I have considered. This fluid element, let us say, is at some distance r. This is at some distance r. And the thickness over here is equal to dr. The thickness over here is equal to dr. And the height of the fluid element, let us say, is equal to dz. The height of the fluid element is dz. Now, previously, what was happening in our subject of statics, what was happening? If I was having some pressure, please observe over here, I was having some pressure over here, and I was having some pressure over here. Since both these points are lying on the same datum level, the pressure was remaining same. That was happening in the case of fluid statics. But now when it comes to vortex motion, these 2 points, since they are having two different radii, therefore they are supposed to have some difference in pressure. Therefore, they are supposed to have some difference in pressure. So first point I have to remember over here is pressure varies. Pressure varies with respect to R and Z. Pressure varies with respect to R and Z, both R and Z, which implies pressure has to be a function of R as well as Z. If pressure has to be a function of R and Z, this implies the value of dP has to be equal to dou P by dou R times dR plus dou P by dou Z times dZ. This is the equation I'm supposed to have. Okay, I hope you understand this equation. If pressure is a function of two variables, then a small change is supposed to be like this. Dou P by dou R times dR plus dou P by dou Z times dZ. Now talking about dou P by dou Z times dZ, we already know the value of dou P by dou Z. How do we know the value of dou P by dou Z? If you recall from the concept of fluid statics, in hydrostatic law, we have already mentioned the value of dou P by dou Z is equal to minus gamma or equal to minus rho G. The value of dou P by dou Z is equal to minus gamma or minus rho G. Now coming to dou P by dou R is something new for you. Dou P by dou R is something new for you. What is the value of this dou P by dou R? The value of dou P by dou R is supposed to be equal to rho omega square into R. This is the equation. Derivation is there for this particular thing. I'm not doing derivation. Derivation is slightly complex. It requires a concept of centrifugal forces and all those things to get this equation. Straight away, I'm giving you the value of dou P by dou R. It is equal to rho omega square R. If I have the value of dou P by dou R and I have the value of dou P by dou Z, from here I can conclude the value of dP has to be equal to rho omega square R times dR minus rho G times dZ. This is the equation of variation of pressure in the case of vortex motion. And this equation is valid for both free vortex motion as well as forced vortex motion. So let me mention over here, this is valid for both free vortex motion and forced vortex motion. This is the equation of pressure you are having. If you only know this particular thing, please understand this. If you only know this particular equation, and you know how velocities are varying with respect to R, that is velocity directly proportional to R for forced, velocity inversely proportional to R for free, everything in this chapter you can get. Okay. So basically, this equation, this particular equation, and this particular equation are the result of integration of this equation, are the result of integration of this particular equation. Okay, if you integrate this entire equation, this will give you pressure term, this will give you velocity term, this will give you datum term. When you integrate it by taking the conditions of free vortex motion, then you are going to get P by gamma plus V square by 2G plus Z equal to constant. When you integrate this equation by taking forced vortex motion conditions, forced vortex motion condition, you are going to get P by gamma minus V square by 2G plus Z equal to constant. Okay, so let me write a note over here. The note over here says that by integrating the above equation, the results in both free and forced vortex motion are observed. Free and forced vortex motion are obtained. The results in both free and forced vortex motions are obtained. Which result am I talking about? I am talking about this particular result and this particular result. These two results are basically by the virtue of this particular equation. If you want to find that out, you can take it as homework. Okay, you can integrate this thing, take it as homework and produce both those equations. Okay. In this particular slide, all you have to do is you have to remember the equation I have mentioned, that is dP is equal to rho omega square into r, rho omega square r into dr, minus you're going to have rho g times dz. This topic is there for GATE also, not only for IES, it is there for GATE also, especially for mechanical GATE. Questions from here have appeared multiple times. Those who are having a doubt regarding the what do you call y-axis, please understand when we are discussing over here this vertical axis, that is z-axis. X-axis and y-axis, both of them are in this particular plane. Just imagine this particular plane is going to have x and y-axis. This is z-axis. Both x and y-axis are taken care by radius. This is also in radial direction. This is also in radial direction. Okay. Moving further. Now that we have seen these equations, I'm going to take up some questions. Question number 1, let us say. This question is worth 2 marks in GATE examination. This is where you are going to see the case of free vortex motion. You're going to see the case of free vortex motion. Imagine, please be patient for some time. Let me complete the question, then you'll understand it better. Imagine that there is a particular passage. One moment, please. Imagine there is a bend in a pipe, something like this. There is some bend in a pipe, let us say, something like this. This entire bend is taking place in some horizontal plane. A bend in a pipe is taking place in horizontal plane. Let us say this distance over here is equal to some 0.2 meters. The distance over here is equal to some 0.2 meters. And this radius over here, let us say this radius is equal to some 0.6 meters. The inner radius is 0.6 meters. There is water flowing over here. Water flowing over here. I'm giving you 2 points over here. Let us say certain point 1 I'm having, certain point 2 I'm having. Point 1 is that the inner bend, inner wall of the bend. Point 2 is at the outer wall of the bend. These 2 points I'm giving you over here. Regarding point 1 and point 2, I'm going to give you the value of pressures, P1 and P2. Let us say the value of P1 is equal to 18 kilopascal. The value of P1 is 18 kilopascal. The value of P2, let us say, is equal to some 20 kilopascal. P2 is 20 kilopascal. This entire bend is taking place in a horizontal plane. Bend in a channel is taking place in horizontal plane. Horizontal plane. This entire thing is happening in horizontal plane. The reason for mentioning horizontal plane is it basically means Z throughout over here is remaining constant. Z throughout over here is remaining constant. Water is flowing in this direction. It is moving like this and coming out. The question further says, assuming the flow in bend, the flow in bend. Now you see, when the fluid is flowing in this particular bend, that at that particular junction, at that particular motion, it is basically observing some kind of vortex motion about this axis. Please imagine there's a particular axis coming perpendicular from this particular point. About that particular axis, the entire fluid body is rotating. So now it is observing some vortex motion. Assuming the flow in the bend. Now please remember this thing. Best example for free vortex motion is flow in bends. Assuming the flow in the bend is free vortex motion. It is free vortex motion. If the bend is observing, if the flow in the bend is observing free vortex motion, the question is find the discharge per unit width in the channel. Unit width over here means width perpendicular to the screen you're having. So basically the area of flow is equal to how much? 0.2 multiplied to how much width is coming perpendicular? Width coming perpendicular is equal to 1 unit. This is the question we are having. Now you see what all things are given to you. You are given the value of P1, you are given the value of P2. You have already, it is already mentioned to you that the value of Z1 and Z2, both of them are same because it is constant. It is mentioned to you that you are having free vortex motion. You are having free vortex motion. Now start thinking that if this is all happening over here, if all this is happening over here, which equation should I apply? Can I apply P1 by gamma plus V1 square by 2G plus Z1 equal to P2 by gamma plus V2 square by 2G plus Z2? Yes, I can apply that thing. The reason is free vortex motion is irrotational flow. In that particular flow, you can apply Bernoulli equation between any two random points. First of all, you take a snapshot of this particular slide. I'm going to create a mirror image of this slide. And in that, we are going to solve the problem. Chaliye, let us start. Let me see how to solve the problem. I'm erasing all these things off. Chaliye. Let us start the solution now. You see, since the flow over here is free vortex, I'm going to start with the concept of free vortex now. Since flow is free vortex, I can say velocity over here is inversely proportional to radius, which implies velocity is equal to some constant divided by radius. Velocity is equal to some constant divided by radius, which implies the velocity at point 1, is equal to that constant divided by r1, and velocity 2, v2 over here is equal to constant divided by r2. This is what we are having. Please remember, whenever you are going to have questions on vortex motion, never think about losses unless he tells you regarding the losses. Please imagine ideal flow only over here. Okay. So we are having this particular condition. Now I'm going to write down, since we are having free vortex motion, I can say the value of P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2. This is what I'm having. So now what I will do, I will straight away cancel Z1 and Z2 over here. The reason for cancelling Z1 and Z2 is because the value of datum throughout is remaining constant. Okay. After having cancelled Z1 and Z2, one minute please. After having cancelled Z1 and Z2, Next thing is, in place of V1 and V2, I'm going to write C by R1. So from here I can imply, that the value of P1 by gamma plus, now in place of V1, I'm writing C by R1. So C upon R1 whole square divided by 2G has to be equal to P2 by gamma plus C upon R2 whole square by 2G, Now do one thing, take the terms, one second, let me do one more thing. I can cancel off G everywhere. I will be remaining with density over here. Take the terms corresponding to R1 and R2 on one side and P1 and P2 on the other side. So what do I have from here? This implies the value of P2 minus P1 whole divided by density has to be equal to 1 by 2 times C by R1 whole square minus C by R2 whole square. So which implies now P1 by P1 minus P2 is equal to how much? P2 minus P1 is equal to how much? 20 kilopascal, means 20,000 minus 18,000 divided by density of water 1000 is equal to half of C square upon R1 over here. Look, what is the radius of this thing? It is equal to 0.6 square minus C square upon, one second, C square upon, what is the radius of this particular point? This is going to be equal to 0.8 square. From here, you can get the value of C. Please obtain the value of C for me from here. Please start. Get me the value of C from here. C is equal to 1.814. Okay. The value of C is coming out to be 1.814. This is the value of C we are having. Please check. I hope all of you are getting C value. We cancelled Z1 and Z2 because I have mentioned that the bend is taking place in a horizontal plane. That means the datum throughout is remaining constant. I'm taking the value of C as 1.814. If the value of C is equal to 1.814, and I want to find out the value of discharge. Now you see how to find the value of discharge over here. Imagine I'm taking some random point over here. This random point is having some random radius. And this is having some velocity v. Let us say this velocity v over here is equal to C by R, which is equal to 1.814 divided by R. This is a velocity v. I want to find discharge, but the problem is velocity is keeping on varying. So I will say, since my velocity is keeping on varying, I'll write differential discharge has to be equal to velocity into differential area. Differential discharge has to be equal to velocity into differential area. What is the differential area? Please observe over here. Since my velocity is varying with respect to radius, I will take a very, very small thickness over here, call it as dr. And let us say this dr is having some width perpendicular to screen. How much width do I want? I only want 1 unit width. So I will say the value of dA over here is equal to dr multiplied to 1 unit width. That is equal to dr only. which implies differential discharge has to be equal to 1.814 divided by R multiplied to how much? dr. This is the value. So complete discharge will be equal to how much? It is 1.814 into integral of dr upon r, ranging from where to where? Ranging from radius r1, that is equal to 0.6, to radius r2, that is equal to 0.8. 0.6 to 0.8. From here, I'm going to get, that implies the value of Q is equal to 1.814 into ln of, you see, integral of dr by r is ln r, ln of 0.8 divided by 0.6. From here, you'll get the value of Q. From here, you're going to get the value of Q. Now, this part is not having anything to do with vortex motion. This part is complete kinematics part. When your local velocity is a function of something, if you want to find out discharge, you should find differential discharge, then integrate in order to get complete discharge. Please get me this value. What is 1.814 ln of 0.8 by 0.6? 0.522. So it is equal to 0.522 meter cube per second. 0.522 meter cube per second. This is the value of discharge we are having in this particular case. See, those who are having difficulty in understanding this vortex motion concept, okay, listen to me for 2 minutes. Don't write anything now. Don't comment anything for some time. Just listen to me for 2 minutes. You see, the problem with fluid mechanics, please try to understand. Okay, there is only one problem which is creating every problem. That one problem is fluid is not a single body. Please understand this thing. Fluid is not a single body. Fluid is a set of infinite layers. And these layers can arrange themselves. They can arrange themselves. For example, please observe over here. If everything was a solid body, it would have been much simpler. Solid bodies are much easier to analyze, but fluid bodies are not that much easier to analyze. Look over here. It is all about visualizing. You see, if I start telling you every visualization, I will complete this entire year, but still I won't be able to finish fluid mechanics. So you have to do something from your side. Imagine I'm having this fluid element moving forward. When it was moving in this particular passage and the flow over here was ideal flow, when it was moving in this particular passage and the flow over here was ideal flow, you take this particular point over here as point A and this point over here as point B. The velocity at point A and the velocity at point B, both of them were same. The velocity at A and B, both of them were same. Now, as this fluid element is keeping on moving over here, now the problem comes in. Imagine this element has taken this position. This element has taken this position. This is point A. This is point B. This is point A and this is point B. Now you see, if this was a rigid body, if this entire thing was a rigid body, then it would have been easier for me to analyze its motion. But now, since it is not a rigid body, it is a fluid, I can divide this also into infinite layers. I can say the motion of this part is independent and this part is different. Both of them are different motions. Since we are able to divide them into infinite layers or infinite parts, the motion analysis becomes slightly difficult. But it is not that much difficult also for you. Already the equations are defined. It has been mentioned that since this is actually a free vortex motion, these 2 points A and B are governed by an equation. What equation is that? That equation is PA by gamma plus VA square by 2G plus ZA has to be equal to PV by gamma plus VB square by 2G plus ZB. This equation is governing these 2 points over here. Also, it is mentioned to you that velocity has to be inversely proportional to R. Just remember these things. Whatever I gave you in the initial part, if you remember that much, you will be able to manage many equations. For example, these two slides, first slide and second slide. If these two slides you are able to understand, okay, let me mention one thing again over here. Velocity over here was inversely proportional to our velocity directly. If this particular slide, if you remember, you will be able to manage any question coming from here. Any question coming from here. See, velocity inversely proportional to r. This is the equation for pressure and velocity and datum. Velocity directly proportional to r, and this is the equation for pressure, velocity, and datum. These two things, if you manage, you will be able to manage any kind of question from here. Okay. After that, finding discharge is not a big deal. You have done this already in kinematics also. I gave you question, laminar flow between two fixed parallel plates. Velocity was varying with respect to y. You are supposed to find out discharge. You were able to do that. Same kind of concept over here also. Okay. Chaliye. Let us now move further. I'll take one question from previous GATE examination. This question was asked in mechanical GATE for 2 marks in 2005 paper. You see, whenever you are having bend in a pipe, you are going to have bend, you're going to have free vortex motion only over here. And regarding the discharge per unit width, you see, this is going to remain same. The width actually means the width coming perpendicular to the screen. The width over here is the width coming perpendicular to the screen. Okay. Let me take one more question. This question is a very interesting question. This was asked in GATE examination for 2 marks. This is 2 mark GATE question. Already been asked. Look over here. This question is slightly difficult. I'll try to make it simple by asking you 3 stepwise question. 3 stepwise question. You do one thing. You try to participate. You also try to solve this question. Okay. Imagine you're having a container. This time the container is a closed container. You're having some closed container. This is a cylinder, closed cylinder. Let us say it is filled throughout with a fluid. It is filled throughout with a fluid. Okay. Completely filled with a fluid. I'm taking a centroidal axis. Suppose I'm choosing a centroidal axis. Suppose I'm choosing a centroidal axis. Let us say this is a centroidal axis I'm having. 1 second. Let us say this is centroidal axis I'm having. About this particular axis, 1 second. This is the ground surface. Cylinder is kept over here. About the centroidal axis, I'm creating forced vortex motion with angular velocity omega over here. It is mentioned to me the density of the fluid is rho. The radius over here is equal to capital R. The radius over here is capital R. And the height over here is equal to capital H. The height over here is equal to capital H. Okay. Now, let us say this particular point is some point A. There is some random point I'm choosing over here, point B. This random point B is at the bottom. It is at the distance of small r. The distance over here is equal to small r. Question number 1. Please try and answer this thing. Question number 1. The pressure at point A is equal to 0. Density is given. Omega is given to you. Small r is given to you. H is given to you. Everything is given to you. You have to find out the value of PB is equal to how much. This is a case of forced vortex motion. This is a case of forced vortex motion. Please try this thing. If the pressure at point A is equal to 0, what is the pressure at point B over here equal to? Very simple question. I have mentioned you everything. Okay. Chaliye. Forced vortex motion. What all do you have to remember regarding forced vortex motion? Velocity directly proportional to r. First thing. Second thing, flow rotational. Third thing, between any two random points, you can't apply Bernoulli equation, but you can apply something similar to Bernoulli equation. Only thing you have to take care in that equation is wherever you see velocity head, in front of that, you're not going to put plus, you're going to put minus. Okay, chali. So solution I'm writing the solution for this question. I know that PA by gamma minus VA square by 2G plus Z has to be equal to PB by gamma minus VB square by 2G plus ZB. This is the equation I'm having. This is ZA, that is ZB. Okay. Now, if you observe, the pressure at point A is equal to 0. This pressure is equal to 0. At point A, the radius is equal to 0. If the radius is equal to 0, recall, velocity is supposed to be equal to r into omega, is it not? Now the radius over here is equal to 0. Automatically the velocity becomes equal to how much? 0. Velocity becomes equal to 0. Okay. At ZB, at this particular point, if I take datum is equal to 0, then this datum is going to become equal to capital H. I hope that is clear to you, that datum is equal to capital H. From here, I can imply that, the value of PB upon gamma has to be equal to how much? PB upon gamma has to be equal to H plus VB square by 2G. H plus VB square by 2G. This is the value I'm having. Okay. Now, what is the value of VB? The value of VB has to be equal to this radius multiplied to omega. So small r into omega. I'm going very slow now. So it is small r into omega, which implies that the value of PB upon gamma has to be equal to H plus small r square omega square divided by 2G, which implies the value of PB has to be equal to, now gamma is rho G, therefore I can write rho G into H plus rho into r square omega square by 2. This is the value we are having for pressure at point B. This is the value of pressure at point B at this particular point. I hope you are able to get this particular pressure. Yes, very good. With respect to the axis, point A is having 0 radius. Okay. Now moving further, once I've got the value of PB, now comes my second question. Look at my second question now. Look at my second question. 1 second. You can take a snapshot if you want quickly. My second question is, once you have the value of PA, sorry, PB, once you have the value of PB, I want you to get how much is the force acting on the bottom plate over here. So the question over here, question number 2, only 2 questions, not 3 rather, 2 questions only. The question is, how much is the force acting on the bottom plate of the cylinder, how much is the force acting on the bottom plate of the cylinder? This is the second question we are having. Now please understand, you see the pressure was equal to, pressure over here at the bottom plate at any radius r was equal to rho into g into h plus rho into omega square r square divided by 2. This is the pressure at the bottom plate at any random radius. Now please observe, the radius is varying from where? The radius is varying from 0 till capital R. If the radius varies from 0 to capital R, that means the pressure also is varying over here. You see rho gh constant, rho omega square 2 constant, but R is variable. Since R is variable, pressure throughout the bottom plate is becoming variable. If pressure throughout the bottom plate is becoming variable, I should say over here, differential force has to be equal to, it has to be equal to pressure multiplied to differential area. Differential force has to be equal to pressure multiplied to differential area. Why am I doing all these things? The reason is because pressure over here is not constant. Pressure over here is a function of which axis? Radial axis. That is why I'm doing all these things. Now please understand, I told you in the first class itself, again I'm repeating this thing. My parameter of interest is a function of something. So accordingly, the area I'm going to take, the differential area I'm going to take should have dr term over here. So imagine when you look on the top view, you're going to see the bottom plate as a disk. You are going to say, let us say bottom plate is a disk over here whose radius is capital R. In this disk, you are going to choose a differential area, which is basically a ring element, This ring element you are going to choose. This ring element over here is supposed to have a radius small r and it is supposed to have a thickness dr. So the value of dA over here, has to be equal to how much? It has to be equal to 2 pi r times dr. It has to be equal to 2 pi r times dr. So now I can say the value of differential force over here has to be equal to how much? Rho gh plus rho omega square r square by 2 whole multiplied to differential area over here is 2 pi r times dr. This is a value of differential force I'm having. Once I have the value of differential force, I can say complete force has to be integration of this thing. So I'm having integral of rho gh multiplied to 2 pi r times dr, ranging from where to where? R is ranging from 0 to, so 0 to capital R plus integral of rho omega square r square by 2 into 2 pi r times dr, again ranging from where to where? 0 to capital R. 0 to capital R. Please start. Please check if you're getting this answer or not. Very good. Chili, many of you are getting this thing. Now, regarding why pressure is varying with respect to R, just imagine a fluid particle over here, when it is observing vortex motion, it is going to have two types of forces. One is by the virtue of gravity, the other is by the virtue of centrifugal. So since it is observing forces in two axes, accordingly pressure also should be in two axes. One is Z axis, one is radial axis. That is the basic idea why pressure is varying with respect to R also. If you are having a static condition, it was observing force only in vertical axis. Therefore it was having pressure variation only in vertical axis. Now rotation takes place, automatically it is going to observe one more force. Therefore pressure variation should take place in both the axes. So this came as a 2-mark question, I think in 2005 paper, mechanical gate 2005 paper. This was regarded as one of the most difficult questions in that particular paper. And still, it is one of the best questions in the entire fluid mechanics curriculum that has been asked in gate examination. Lengthy question also. The question did not talk about this particular part. Straight away, he gave this particular case and said, what is the force acting on the bottom plate? The question straight away gave this particular case and said, what is the force acting on the bottom plate? You are supposed to find out that force which is supposed to be pressure into area. First, you have to think about pressure at the bottom plate. When you think of the pressure at the bottom plate, you will get pressure is a function of radius. Since pressure is a function of radius, then you have to use your logic. Since pressure is not a constant, it's a function, I should say force is dF is equal to P times dA. Then you are supposed to move forward from there. There is going to be no horizontal component of force on the plate. And as far as rectangular section is concerned, if the cross section is rectangular, it becomes extremely difficult because pressure variation is defined with respect to radius. The value of radii are going to be different at the corners, are going to be different at the walls. So it becomes extremely difficult. Still, you can find it out. Mechanical gate question. Chili. This was mechanical gate question. Let us move forward now. Now, last topic in vortex motion. After this, within 5 minutes, I'll summarize entire vortex motion. This is the last topic. After this, within 5 minutes, I'll summarize the entire vortex motion. Your entire gate examination, IAS examination will deal within those 5 minutes, only 5 minutes. Okay. So please be patient. Let us see the last topic now. The last topic over here is regarding some standard results in forced vortex motion. This is talking about standard results in forced vortex motion. Forced vortex motion. Okay, these results, please be careful, are only valid for which vortex motion? Forced vortex, not for free. I'm underlining only forced vortex motion. Two standard results we have to discuss over here. The first result is regarding the concept of isobar. Isobar is also, if you remember, isobar is also called as lines of constant pressure. Okay, what will happen to isobar in the case of forced vortex motion? Let us see. Imagine you are having some container. Imagine you're having some container. Let us say this is a container you're having. One second. Let us say this is a container you're having. In this container, you're having some fluid present. Suppose there is some fluid present over here. There is some fluid present over here. Suppose that level of fluid is something like this, horizontal level, something like this. This is the level of fluid present. Now, so I'm not shading the downward portion for some reason. Please wait. Let us say I'm taking a particular axis. I'm taking a particular axis, a central axis, let us say. And about this central axis, this is central axis, let us say. About this axis, I'm creating some forced vortex motion. About this axis, I'm creating some forced vortex motion. Forced vortex motion. Okay. When I create forced vortex motion, what will happen? The line of constant pressure, which was previously over here like this. This was a line of constant pressure previously. This will not remain as the line of constant pressure. If you imagine, you take a bucket filled with water, you create some kind of a whirlpool using your hand. That is a case of forced vortex motion. You're using your hand to apply some torque over here on that particular fluid. You might find that the fluid interface is now going to bend somehow. The interface will now bend. Let us say the interface is now getting bent. So imagine you're going to have a bend kind of interface. You're going to have a bend kind of interface, something like this. This is how the interface is going to become. The fluid will take, one second. One moment, please. The fluid will take this particular position. The fluid takes this particular position. The line of constant pressure, which was previously this horizontal line, has now become this particular line. This is the line of constant pressure you're having. Along this particular line, the pressure value is going to be equal to P naught. The pressure value is P naught. The other lines of constant pressure will come parallel to this thing. What do I mean by that? Imagine the other lines of constant pressure, they are supposed to be parallel. That means you're going to have lines of constant pressures. One second. All of them are going to be parallel. This is how you're going to have lines of, all of them are supposed to be parallel. Probably my diagram is not showing that much parallel nature, but please imagine all these lines of constant pressure are going to be parallel. Let us say this is P1, this is P2, this is P3 and so on. P3 and so on. Okay. So first point over here, that is regarding lines of constant pressure, lines of constant pressure or isobars. Isobars. What do you have to remember regarding this? You have to remember A bit. I'm trying to write down in a way you can memorize easily. Okay, A bit. Parabolic. These are all going to be parabolic in nature. All the lines of constant pressure in the case of forced vortex motion are going to be parabolic in nature. Second thing, they are supposed to be governed by a particular equation. They are supposed to be governed by a particular equation. What equation is that? Please observe this thing. This equation is important. You can get questions from here. especially IES people, direct question is possible from here. Okay. Imagine this particular point I have taken. This point, let us say some point A I have chosen, example sake. I have chosen another point over here, some point B. Both A and B are lying on line of constant pressure. Let us say this distance over here is some distance R, and this vertical distance over here is some distance H. My aim over here is to find out the relationship between R and H. Okay. How to find out the relationship between R and H? I'll give you a hint. You take it as homework. Straight away result I'll write over here. To find out the relationship between R and H, what I will do, I told you, the most important slide is this particular slide. In this particular slide, you put that equation PA by gamma minus VA square by 2G plus ZA is equal to PB by gamma minus VB square by 2G plus ZB. PA and PE both will get cancelled off because they are on line of constant pressure. From there, you are going to get the result. Directly, you can memorize the result. The result is H is equal to R square omega square divided by 2G. H is equal to R square omega square. Now you see over here in this particular equation, you can see H is proportional to R square. Since H is proportional to R square, I can say what kind of curve you are going to have? Parabolic curve you are going to have. So lines of constant pressure are going to be parabolic in nature. This is regarding the first point. Second result we have to know. Second result over here we have to know, that is something known as paraboloid. Second result over here is paraboloid. What is this paraboloid? Paraboloid is volume of revolution of the parabola at interface. Parabola at interface. Now you see over here, this interface, you see I have shown over here, this is interface. This interface is a parabola. But imagine a 3D picture. In a 3D picture, what is going to happen? You are not going to have a line. You are actually going to have a surface actually. You are basically having a complete parabola in 3D picture. That is basically, now please try to imagine. Let me draw a picture so that you can understand this easily. One moment, please. So if you, one second. If you imagine that parabola, if you create a 3D picture of that thing, it is going to form some kind of a cup. It is going to form some kind of a cup. That particular cup is known as your paraboloid. That cup is known as a paraboloid. One second. That cup is known as paraboloid. 1 minute, please. Let us say this cup is over here known as paraboloid. Now this paraboloid is going to have how much height? Let us say the height of this paraboloid. The complete height of the paraboloid is equal to capital H. And the complete radius of this paraboloid is equal to capital R. Complete height is capital H, complete radius is capital R we are having. Now, the volume of paraboloid is equal to half the volume of circumscribing cylinder. See that what is the meaning of circumscribing? You might have studied something on a circumcircling, the concept of triangles. Circumcircle was there. That means if you're having a triangle, the circle which is completely enclosing the triangle is called a circumcircle. Similarly, this parabola will fit completely inside a cylinder. That cylinder also will have a height h, and that cylinder will also have a radius r, which implies the volume of this paraboloid, has to be equal to half. What is the volume of circumscribing cylinder? The volume of circumscribing cylinder is equal to pi into r square into h. This result you have to remember. So in this particular slide, I'm not doing derivations, but I'm helping you with everything, whatever is required over here. Two things are required over here. One is line of constant pressure. You should know, just imagine you are creating everyone must have done this thing in bathroom, right? You must have created a whirlpool in a bucket. When you create a whirlpool in a bucket of water, that is basically forced vortex motion, approximately forced vortex motion. Okay. Now, in that forced vortex motion, you might have seen that you are going to have lines of constant pressure which are parabolic in nature. The surface is not going to be parabolic. That equation I have mentioned over here. Equation is important. You can have questions coming from here. Second thing. Now, the parabolic surface is actually a volume, complete 3D picture. If you see, it is going to be a volume, like a cup. That cup is going to have a height capital H. It is going to have a radius capital R, let us say. What is that volume of that cup? What is the volume of a cup? That volume of a cup is going to be equal to half the volume of circumscribing cylinder over here. That is half pi r square h. Okay, these are the standard results. With this, we complete the concept of vortex motion. Now, as I promised you, how to remember the vortex motion concept. Okay, I'll give you a hint and you take it as homework for how to memorize all these things. If you want, you can take a snapshot of this particular slide very quickly. Please be quick. What are the applications of these things? Sir, paraboloid is a vacant space. Yes, Yash Patel, paraboloid is a vacant space over here. Very good, Venkatramana. See, H should always be measured from this particular point, that is the vertex of the parabola. Okay, from this particular point, you're supposed to start measuring H, and you're supposed to start measuring R from the axis about which you're creating rotation. Okay, Chali, look over here. What do you have to remember? I'll tell you over here. When you're writing short notes, please create a table. Over here, you write free vortex motion. Over here, you write forced vortex motion. Three differences you are having. First difference, velocity over here inversely proportional to R, velocity over here directly proportional to R. Second difference, the flow over here is irrotational flow. Immediately because of irrotational flow, what do you get? You get the result PA by gamma plus VA square by 2G plus ZA is equal to PB by gamma plus VB square by 2G plus ZB. This is the result. Over here you say omega is also equal to constant. Now, the flow over here is rotational. If the flow over here is rotational, I'm not going to get this equation. What am I going to get? I'm going to get PA by gamma minus of VA square by 2G plus ZA has to be whatever it is. This much part, just this table is sufficient to solve every previous gate question that has come in vortex motion. Only this table is sufficient to solve every previous gate question that has come in vortex motion. Apart from this, you are going to have a common point. What is a common point? dP is equal to rho omega square r times dr minus rho g times dz. Then for forced vortex motion, there are two things. First thing over here, you can see that parabolic isobars are going to be there. The equation is governed by H is equal to R square omega square divided by 2G. If you still have a confusion, H is from vertex R is from centroidal axis. Not centroidal, rotational axis, not centroidal. Sometimes you can have different rotational axis. Rotational axis. R is from rotational axis. Second point you have to remember is the volume of paraboloid. Volume of paraboloid has to be equal to half the volume of circumscribing cylinder, half pi r square h. Entire vortex motion finished. I don't even think I have taken 5 minutes for this. This much is sufficient. You can manage any question from here. Okay. See, whenever you are preparing, you should always think of these kind of techniques. Okay. So whenever you are doing any chapter, you please, not any chapter, rather any subject, you please write short notes for yourself. I'm telling you, without short notes, you'll find the subject is very bulky. As a matter of fact, when you write short notes, you will feel that a subject can be completely encapsulated in some 10, 15 pages. That will be sufficient for you. I'm telling you, before you are going for examination, you won't have that much time to go through all the slides, all the notes and all. That is not possible. Just imagine 3, 4 days before examination, can you open the notes? It's not possible. What you can open is only short notes. So see to it that you're preparing short notes every time. Okay, this much is sufficient for vortex motion. I have taken some good questions also. 2 questions I have taken. One was for free vortex motion. The other was for forced vortex motion. The other was for forced vortex motion. And those were the highest level of questions that have appeared in GATE examination. Now, as far as civil examination is concerned, this topic is there in civil examination, but questions have not come from here in GATE. In IAS, questions from here have appeared. It is there in civil syllabus. Okay, don't think that it is not there. It is there in civil syllabus. Questions have not appeared that much. But if you start thinking like that questions have not appeared, they will never appear. That is also wrong, because recently in GATE examination, questions are starting to appear from new topics also. Okay, chaliye. With this, I complete the concept of vortex motion. Now I'm starting the next chapter. The chapter's name now is momentum equation application. Momentum equation and application. Momentum equation and application. Okay. Please keep quiet for some time. I'm already moving very slow. Okay. In your literature, this chapter is chapter number 6 in the textbook you got from the academy. This is chapter number 6. In my notes, I would regard it as a part of fluid dynamics only. I told you when I started fluid dynamics that it is going to have 2 parts. One part is Bernoulli equation chapter, that is energy equation application. And the second part of fluid dynamics is momentum equation application. Let me give you the basic idea of what we are going to do over here. Okay. Recall in Bernoulli equation chapter, we were talking about energies. In this particular chapter, we are going to talk about momentum. And by the virtue of momentum, we are going to get something called as force now. You see, when you're having a particular container in which you are having a gate, there was a fluid. How much was the force acting over here? That force, if you recall, it was equal to gamma into area into h bar. That force was hydrostatic force. It was under static condition. But what if the fluid is flowing? What if the fluid is flowing? Imagine that you are not having a gate which is in contact with a static fluid. Imagine you are having a plate and there is a jet of fluid coming over here and striking. The fluid is not static anymore. The fluid is in dynamic condition. How to identify the force in this particular condition? That is what we are going to study in momentum equation. So over here, the basic idea is we will talk about how much is the force acting when the fluid is in dynamic condition. Because when the fluid is in dynamic condition, only then you can talk about momentum. Static condition was very simple. We have discussed hydrostatics from here. It was very simple. This is slightly complex. But you see, the complexity will come only if you are having difficulty in the mechanics part. If you are comfortable with the mechanics, then this complexity will not be there. Okay? Shall let us start the chapter now. One moment, please. To understand this thing, I'm going to start first of all with the equation we have studied in our mechanics, which says force is equal to dmv by dt. Force is equal to dmv by dt. mv over here is known as linear momentum. mv is known as linear momentum. So basically force is equal to rate of change of linear momentum. Please remember, linear momentum, which is represented by capital P vector, is a vector quantity. It is a vector quantity. Now from here, we can imply that F times dt has to be equal to dmv. F times dt has to be equal to dmv. Now this f dt, which is the left hand side of this equation, f dt over here, it is called as impulse. It is called as impulse. The value of impulse has to be equal to how much? It has to be equal to change in linear momentum. Change in linear momentum. Impulse has to be equal to change in linear momentum. Okay. This entire equation over here is known as your impulse momentum equation. This entire equation is known as impulse momentum equation. And from this impulse momentum equation, you get something known as law of conservation of momentum. This is impulse momentum equation. From here, you get something known as law of conservation of momentum. All these things are a part of your mechanics. But the problem with mechanics over here is generally people are not that much comfortable with the concept of impulse momentum equation, because generally, what happens is last chapters in your syllabus, you don't concentrate that much. Okay? But what we are going to do is we are going to use this particular equation only to develop the equation of force whenever the fluid is moving. The question over here is, how are we going to apply this particular equation in fluid mechanics? Please keep quiet for some time. Sound is low. Voice is low. Are your voice problem? 1 minute, please. Lagging also. Yes, I hope it is fine now. Okay, I'm going to continue now. This is practically in front of my face, so I can't do anything further. Okay. Chaliye, I'm moving further now. I'm moving further. One second. In my audio setting, everything is at maximum. Everything is maximum. You please check your audio settings also once. Those who are having difficulty. I'm continuing now, please. Okay. Don't comment for some time. Just listen to the story for some time. You will appreciate the subject. Within 5 minutes, you'll be able to understand what exactly is happening. Where is mechanics different from fluid mechanics? Remember this thing. Whenever you study fluid mechanics, please try to understand where is fluid mechanics and mechanics differing. That much is sufficient. If you understand that, you'll understand the subject very easily. For example, in Pascal's law was valid in the case of fluids. It is not valid in the case of solid. The reason is solid is a single body, whereas fluid is a set of infinite bodies stacked one below the other. So therefore, what was happening? Every layer was transferring the pressure to the next layer without any loss. That is why Pascal's law is valid. Similarly, coming to continuity equation, we never spoke about mass, we spoke about mass flux. We never spoke about volume, we spoke about volume flux or discharge. The reason is fluid is continuously flowing, is it not? Similarly, in energy equation or Bernoulli equation concept, in your mechanics, you talk only about two equations. Which two terms were there? Kinetic energy, potential energy. But our subject was talking about three things: kinetic, potential, and pressure energy. See, you see how the subject is slightly changing. From mechanics, you're shifting slightly to fluid mechanics. That is why for fluid mechanics, mechanics should always be very strong. Okay? In momentum equation, now listen carefully what we are doing in momentum equation. I am having this equation F is equal to dmv by dt. Whenever a flow is taking place, imagine there is some particular nozzle. In this particular nozzle, there is some flow taking place. And I'm holding this nozzle with some support over here. I'm holding this nozzle with some support. There is some flow taking place over here. Now what happens? I see that with respect to space, my velocity is changing. For example, my velocity over here is v1, my velocity over here is v2. With respect to space, my velocity is changing. But my mass also is changing with respect to time. That means I'm having some amount of mass entered over here. After some time, that mass is somewhere forward over here. So now what I'm going to do, in this equation of force, which is dmv by dt, I'm going to give the mass variation to time. Please try to understand this thing. In the case of solids, mass was remaining constant. There was no mass flux. But in fluid, since there is mass flux, I'm going to give this mass variation to time over here. If I give mass variation to time, now the equation is going to become force has to be equal to d of, now you see I'm giving mass variation to time, I'm going to get m dot into v. This m dot into v over here, again a vector quantity, this over here is known as, you see, m was mass, m dot was mass flux. Similarly, mv is momentum. M dot into v over here is known as momentum flux. It is known as momentum flux. Try to understand this again. In the case of solids, generally what we do, we take mass outside. We say dv by dt, so we get mass times acceleration. That was happening in the case of solids because mass was remaining constant for a particular body. But in the case of fluids, what is happening? In the case of fluids, mass is continuously flowing. That is why I should define how much mass per unit time is flowing. Since I have to define how much mass per unit time is flowing, I'm going to give the mass variation with respect to time over here. So this dt term will act for mass over here. So therefore, now I will write m dot, then multiply to v. This m dot into v over here is called as momentum flux. Now force, which was equal to this much, will now become equal to d of m dot into v. D of m dot into v. This is the equation we are going to use mostly. Okay. Now to understand this better, let us now talk about. You can take a snapshot of this particular slide, and please be patient. If you are not following, you please be patient. Once you see an example question, you'll understand everything. It will take some time because I know most of you have not studied this concept at all in your university examination. Generally, people leave this chapter completely. Mass flow rate is constant. I accept it. But mass is varying with respect to time. Chaliye. Let us move further. See, mass flow rate is constant, accepted, but mass is varying with respect to time. You please be patient. Once you see an example problem, you'll understand this thing. Wait on. Now we are defining over here the concept known as momentum flux. Momentum flux. This momentum flux is represented by m dot into v. Is represented by m dot into v. The net force acting has to be equal to delta m dot into v vector. M dot into v vector. Net force is equal to m dot into v vector change. This implies, let us say, net force in x-axis has to be equal to delta m dot into velocity in x-axis, which is equal to m dot into velocity in x. Let us say at final section. What do I mean by final section? This, let us say, is my final section. Okay, minus m dot into velocity in x at initial section. What do I mean by initial section? This, let us say, is my initial section over here. This is how I'm going to write the equation of force. Likewise, for any axis, let us say sigma fy, if you write, then sigma fy has to be equal to delta m dot into velocity in y. Again, m dot into velocity in y in final minus m dot into velocity in y initial. This is the equation we are going to follow to find out the value of force in our subject. But there is one more problem. The problem over here is the velocity in this equation is corresponding to average velocity. It is corresponding to average velocity. Vx over here is average velocity. That means I have taken the average velocity for this entire section. Average velocity for this entire section. If you recall, if the velocity profile is non-uniform, there is a possibility of some error getting created. In order to overcome that error, I have to again define a correction factor. That correction factor is momentum flux correction factor. Momentum flux correction factor. Correction factor. This is represented by beta. Okay, remember last chapter you are having kinetic energy correction factor. Similarly, you are having momentum flux correction factor. What is the reason for this momentum flux correction factor coming in? The reason is the velocity in the equation of momentum flux. Look at my cursor. The velocity in the equation of momentum flux corresponds to which velocity? It corresponds to average velocity of flow. If it is average velocity of flow, whenever you have a non-uniform velocity profile, error will be created. To overcome that error, you are supposed to have momentum flux correction factor. So you can say in non-uniform velocity profile, an error is created, an error is induced, error is developed since velocity corresponds to the average at the section, average at the section. Therefore, actual momentum flux has to be equal to how much? Actual momentum flux has to be beta times m dot into v. This should be the actual value of momentum flux. Now the question is, what is the formula for beta? If you remember the formula for alpha, remembering the formula for beta is very simple. The formula for alpha was 1 by AV cube. This will be 1 by AV square. Integral, it was U cube dA. This will be U square into dA. U square into dA over the entire area. A over here is cross-section area. V is the average velocity. U is the local velocity. And dA is a corresponding area for local velocity. All these things I have discussed over there also in alpha. I'm not writing them again over here. Formula you have to remember. This formula you have to remember. Moreover, some results you are supposed to remember. What is the result you are supposed to remember? The result you are supposed to remember is in laminar flow through pipe. In laminar flow through pipe, the value of beta is equal to 4 by 3. The value of beta is equal to 4 by 3. Okay. And again, the value of beta in laminar flow will be always greater than beta in turbulent flow. I have discussed why it happens in alpha also. If you want, still later on when we discuss the concept of turbulent flow, we can discuss this again, this thing. Okay. And the value of beta is equal to 1 in uniform velocity profile. Uniform velocity profile. The value of beta is equal to 1 in the case of uniform velocity profile. This is regarding the equation of momentum flux we are having. And the equation of momentum flux. VP stands for velocity profile over here. VP stands for velocity profile. Okay. This is velocity profile, please. Velocity profile. Now moving further. Try to imagine this question again. Try to imagine this question. If you're having a mechanics question, think from mechanics point of view. Just imagine if you're having some surface, there's a block, you're applying some forces, F1, F2, F3. Likewise, let us say this is a block you're having. I come and ask you that what is the acceleration of this block? To find the acceleration of this particular block, you will follow 2 steps. Okay, that is a standard way, is it not? You'll follow 2 steps. The first step is analyzing. That analyzing part is called as free body diagram, very important part. So what you'll do, you'll draw a free body diagram over here. You'll see it is having some weight mg, it is having some normal over here, F1 over here, F2 over here, F3 over here. Let us say some friction over here, all those things. This is analyzing of this body. What are the forces acting on this particular body? This will be your first step. Then what will be the second step you are going to have? The second step will be you are going to use your Newton's second law and you are going to write summation of force in x has to be equal to mass times acceleration in x. Likewise, summation of forces in y is equal to mass times acceleration in y. You are going to write this thing. Something similar we have to follow in our subject also. When we are having a nozzle, example, I'm taking a simple example of nozzle over here. Let us say a support over here. My question, I come and ask you, what is the reaction at the support? What is the reaction at the support, I ask you. If I ask you what is the reaction at the support, You will say, I can get the reaction at the support by the equation sigma fx is equal to delta m dot into velocity in x. You see, in mechanics, look at my cursor. Where is my cursor? Look at my cursor. In mechanics, you are writing sigma fx is equal to mass times acceleration. A similar kind of equation in fluid mechanics you are having is sigma fx is equal to delta m dot into velocity in x. This is a similar kind of equation. Now the question is, before writing this equation, you should have something similar over here also. I hope you are following. Okay. ये है equation. Equation से पहले analysis आना चाहिए. You are supposed to get some analysis before the equation. That is done by the next topic we are having, which is known as control volume diagram. It is known as control volume diagram. So right now we are in a need of something like free body diagram in our subject that we are going to define in the next slide. That particular diagram, which is helping you analyze what all forces are acting, that diagram is called as your control volume diagram. Once you have drawn control volume diagram, then you can proceed forward to write this particular equation. So please understand, to solve any equation, there are two steps. One step is analysis step, which will have no equations, which will only have a diagram to help you visualize what are the forces taking place. After this analysis step, you're going further to the next equation. Using this particular diagram, you're going to write equation. देखिए, using this diagram, you're able to write this equation. Similarly, using this diagram, you'll be able to write this particular equation. Then whatever is unknown, you will find out from that particular equation. I hope you are following this. Again, if you are not following, please be patient. You let me do my work, you will understand. Okay, you will understand after some time. Now I'm going to define this control volume diagram in this particular slide. Let us define control volume diagram. Control volume diagram. Now, what is this control volume diagram? First of all, it is an imaginary volume of flow considered on which the force interactions take place. Force interactions take place. It is an imaginary volume of flow considered on which the force interactions are taking place. This is a control volume. Now, one important thing regarding control volume is this control volume will have a boundary because you are taking an imaginary volume. Imaginary, it can be real also, it can be imaginary also. Okay. You are going to have some boundary to this control volume. That boundary of control volume is called as control surface. So the boundary of control volume is known as control surface. This control surface is important. Okay, this control surface is important. Now we are going to see the rules for drawing the control volume diagram. There are some rules that you have to follow in order to draw control volume. See, by control volume, just imagine it is something like free body. हमारे सब्जेक्ट का फ्री बॉडी, उसका नाम कंट्रोल वॉल्यूम है. ठीक है, आर सब्जेक्ट्स फ्री बॉडी इज कॉल्ड एज कंट्रोल वॉल्यूम. ठीक है, फर्स्ट रूल, कंट्रोल वॉल्यूम can have any shape or size, but it should be drawn such that now this control surface I told you is very important. Now he will come into picture. It should be drawn such that control surface is perpendicular to inlet and outlet velocity vectors. What do I mean by inlet and outlet velocity vectors? You see over here. This is my inlet velocity. This is my outlet velocity. My control surface, let us say, this is my control volume over here. This entire thing is my control volume. You see my control surface is perpendicular to inlet and outlet velocity vectors. That is the first rule you are having. Second point over here. Second point. Okay, I'll write CV from here onwards for control volume. Okay. Second point over here is control volume can be static or moving. You can have moving control volume, you can have static control volume, anything is fine. But there is a condition now. What is the condition? It should not be accelerating. It should not be accelerating. Should not be accelerating. The control volume should not be accelerating. Here, some of your doubts will get cleared. Some of you have mentioned some doubts which I did not address previously. Okay, which I did not address previously. The doubt will get cleared over here. What was the doubt? I think some of you have asked that why are you considering only time variation for mass? Why are you not considering time variation for velocity, whereas velocity can also vary with respect to time? Accept it. But now, right now, what we are looking for is actually a steady flow condition. Right now, what we are looking for is a steady flow condition. In steady flow condition, velocity can vary with space, but velocity is not supposed to vary with respect to time. That is why I have given this the time variation to whom over here? Mass. But when I say time variation to mass, don't think that mass flux is changing. It only means mass per unit time. This m by dt means mass per unit time. Okay, that is constant, of course. The change over here of velocity should be taken with respect to whom now? Space. Okay. Now what will happen if the entire system starts accelerating? First thing first, if entire system starts accelerating, it becomes a non-inertial frame of reference. You might have studied in your mechanics, it becomes a non-inertial frame of reference. Your Newton's law is not going to be valid in that particular case. Since your Newton's law is not valid, even whatever equation you are having for momentum flux, that equation also becomes invalid. Okay? So please remember this thing, control volume can be static or moving, but it should not have any acceleration. This is the second point. Now coming to third point. Third point is directly taken from your free body diagram concept. In free body diagram, recall in this slide, the surface below was behaving as a support. But when you were drawing the free body diagram, you removed the support and you showed a reaction. That is a rule in free body, that every support should be removed and corresponding reactions are supposed to be shown. Same rule over here is going to be applied. Every support on control volume is removed and corresponding reaction forces are shown. This is one more thing. You are supposed to remove the supports and you are supposed to show the corresponding reaction forces. These three rules you have to remember. Then you can draw control volume. Once you have drawn control volume, you can apply the equation of momentum flux, something like this. Once you apply the equation of momentum flux, whatever is the unknown thing you will get. Let us try to understand this with a problem. I might take extra 10 minutes beyond the class time today, but please be patient with me. Once you understand this problem, you have understood the concept of momentum equation. And from this problem, whatever I'm discussing, many times, many questions in both mechanical and civil, GATE and IS, every examination have appeared. So what I'm discussing is equally important for GATE IS, equally important for mechanical and civil. Okay, let us take a problem. And you have to help me with the solution. So be ready with the calculators and try to solve along with me. When I'm writing a particular step, you also participate from your own side and write those steps, try to solve it. Okay. Imagine that I'm having a bend in a particular pipe. Let us say I have a bend in a particular pipe. Let me draw a diagram. 1 second, please. One second. Suppose there is a fluid flowing. Let us say water is flowing over here. Let us say water is flowing over here. This angle of the bend is equal to 60 degrees. Very, very common question. Bend in a particular pipe. Now to support this bend, you are using some kind of a support over here. There is some support over here. Let us say S. It is given that this is some section 1. This is some section 1. At section 1, the value of cross section area A1 is equal to, let us say, some 0.2 meters square. Cross section area is 0.2 meters square. The discharge of flow over here is, let us say, equal to some 200 liters per second. The pressure at section 1, let us say, is equal to some 60 kilopascal. Okay. Section 2, let us say this is section 2. The cross section area A2 over here is equal to, the cross section area A2 over here is equal to, let us say, some I'm just taking some random numbers, okay? Some random numbers so as to create question. 0.05 meters square is the cross section area. The pressure P2 over here, let us say, is equal to some 15 kilopascal. Okay, 15 kilopascal. Don't apply Bernoulli equation. Probably you'd get a different value of pressure. So as to create question, I'm just taking some random values. Okay, this is just for random values. All this is mentioned. Okay, the question asked over here is, if this is my x-axis and this is my y-axis positive, x-axis positive over here, y-axis positive over here, the question over here is find the net force acting at support S. Support S. What is the net force acting at support S? Very quickly, please draw a rough diagram of this question. You are going to practice with me along with me only. Chaliye, be quick. Now I'm starting the solution. I hope you have taken down all these things. The flow is taking place in this direction, coming out from here, let us say. My solution, I told you previously also, my solution is supposed to talk about what you call, first of all, it is supposed to start with an analysis part, which is a control volume diagram part. After control volume diagram, I'm going to write whatever equations are required. So let us start with the control volume. Again, I'm telling you, please treat the control volume as, one second, as a free body diagram over here. This is a slide for question. I'm starting the solution from this slide. 1 minute, please. Okay. I'm starting with control volume over here. Now you see, I'm having some inlet velocity over here. I'm having some outlet velocity over here. I can take this entire thing itself as control volume. Most of the time this will happen. Whatever is a diagram shown to you, that itself can be taken as control volume. So this entire diagram itself can be taken as control volume. So don't worry. This control volume becomes very easy in many questions. In almost every question in previous GATE IES, whatever diagram is given to you, same diagram was your control volume. So let us say my control volume is something like this. Okay, this might not be as neat, but please adjust. This is my control volume diagram. I know that this angle over here is equal to 60 degrees. This angle is equal to 60 degrees. Now, what are the rules of control volume? Recall. Third rule straight away you recall. Third rule. Remove all the supports and show the corresponding reaction. That means I'm not supposed to show any support over here. Let us say at this particular point, I'm supposed to show reaction. I realize that there can be a reaction in X, there can be a reaction in Y. So let us say I'm having some reaction in X and in Y. This is RY, this is RX. Now, many times people ask me this doubt. I think you also have this doubt, that how to take the direction of this RX and RY. I say whenever these kind of questions are asked, you take direction up to you only. You take left hand side or right hand side for RX. You take upward or downward for RY. No problem. If your direction sense is wrong, automatically the answer will correct you. If your direction sense is wrong, your answer will correct you. Don't worry about that thing. Okay, next thing. At this particular point, he has said that there is some pressure acting. If there is some pressure present over here, there has to be some pressure force. There has to be some pressure force. So basically this entire thing, what I'm showing you, is taken out of a particular piping system. So just imagine the fluid in front, the fluid before. Look at my cursor. There must have been some fluid over here. That fluid over here is going to apply some pressure force. Remember, pressure force will always be compressive in nature. That means this is going to be equal to P1A1. Similarly, at this particular point, again, there is some fluid present over here. Even though the flow is taking place in this direction, the fluid present over here can only apply compressive pressure force. Therefore, this is supposed to be P2A2. This is many times difficult for many students. To accept that why is the pressure force acting over here. Remember, pressure force is compressive in nature. That means whatever is the pressure over here, it may be true that flow is taking place upward, but the fluid elements in my scope are going to get compressed only because of the pressure. Okay, so you're going to have P2A2 over here. Next thing, you're going to have certain velocity over here, V1, let us say. You're going to have certain velocity over here, V2. Now this completes my free body diagram, control volume diagram. But there is one more problem. Right now, I do not know the value of V1 and V2, but I can get the value of V1 and V2 very quickly. Remember, every question somewhere or other, it will deal with continuity equation. How to get the value of V1? I can say the value of V1 is equal to Q upon A1. That is equal to Q is equal to 0.2 meter cube per second divided by A1 is equal to 0.2 meter square. So this is equal to how much? V1 is equal to 1 meter per second. V2 is equal to Q upon A2. That is equal to 0.2 upon 0.05. That is equal to 4 meters per second. 4 meters per second. Shall we quickly finish this off? Remember, pressure force is always compressive. If you are having a surface like this, the pressure force has to be a compressive normal force. Just remember this much. Regardless of the direction of flow, you are supposed to take pressure force compressive only. Okay? Shall we quickly take this down? Now what do I have to do next? I have to write the equation. I have to write the equation now. The equation I'm writing is summation of fx, let us say. First of all, I'm writing the equation summation of fx. Summation of fx has to be equal to delta m dot into velocity in x. This is the equation I'm having. Now look over here. What are the forces acting in x-axis? The forces acting in x-axis. This is acting in x-axis. This is acting in x-axis. He will have a component in x-axis. He will have a component in x-axis. You see over here, this is 60 degrees. He will have a component x-axis. You see, I have chosen this as positive x. I have chosen this as positive y. So what are the forces in x-axis over here? P1 times A1, I'm going to have in positive x. Rx is in negative, so minus Rx. Next, P2A2 is going to have a component in x. That component in x is going to be P2A2 cos 60. That is in positive x only, plus P2A2 cos 60 degrees. P2A2 cos 60 degrees. Left hand side is summation x, finished. Has to be equal to m dot into velocity in x final. M dot into velocity in x final. So it is m dot into, now look over here carefully. Look over here carefully. Velocity in x final basically is, this is my final section. The component of velocity in x, the component of velocity in x over here is in this direction. Look at the diagram. The component of velocity in x is in this direction. So I'm going to have velocity in x final is negative first of all. Multiply to what? V2 into cos 60. Negative V2 cos 60. This is my final m dot minus initial m dot into velocity in x. I hope you're following. This is basically m dot into velocity in x final minus m dot into velocity in x initial. अब देखिए final section में you are having negative direction. That is why I wrote negative. Then this minus. Next m dot. M dot. What is velocity in x initial? Velocity in x initial is positive only. So v1, that is equal to v1 over here. This is what I'm having. Okay. This is the equation, total equation I'm having. Now from here, I want only the value of Rx. If I want only the value of Rx, I can write Rx is equal to Rx. Take Rx on one side. It is equal to P1A1 plus P2A2 cos 60. Calculations might be slightly lengthy. Okay, don't worry. This is also negative. This is also negative. If they come on one side, they'll become positive. So plus m dot common to V2 cos 60 plus V1. This entire value will be equal to the value of Rx, which implies the value of Rx is equal to P1. कितना था P1? 60 kilopascal. So 60 into 10 power of 3, A1, everything I'm writing in SI units. Okay, I'm writing everything in SI units because yesterday someone has told me that units confuse you. I say whenever units confuse you, you act very smartly and write everything in SI unit. Probably one or two, steps extra will be required, but you will get the correct answer. A1 is equal to 0.2 plus P2 over here is equal to 15 into 10 power 3. A2 is equal to 0.05. Cos 60 is equal to half. Plus m dot is equal to, m dot is rho q. So rho is 1000. Q is 0.2. V2 is equal to 4. Cos 60 is equal to half. Plus V1 is equal to 1. This is the value I'm having. If you calculate the value of Rx, it comes out to be equal to, you can check this value. You do calculation, please. Shall you do calculation? Someone give me the answer, okay? I'm in no mood of calculating now. 12,675 someone is getting. 12,975 someone is getting. ठीक है 12,975 will take. ठीक है. This is 12,975 newtons, which is equal to 12.95. 12.95 kilonewtons. I know I'm beyond time now, but I'm going to still move further for 10 minutes. Please bear with me. You are going to write the equation Fy. Once you finish, I will write the equation. Okay, stop commenting on the answer. M dot is basically density into discharge. Density, I know for water is 1000. I mentioned initially that the working fluid is water. Discharge is equal to 280 per second. That is equal to 0.2 meter cube per second. Is it not? So from there, I got the value of m dot. Chili. Let us say everyone got the answer 12.95 kilonewton. I got positive answer over here. That means whatever direction I have chosen for Rx is a correct direction. Whatever direction I've chosen for Rx is a correct direction. Now I want you to write the entire equation for sigma F. That means from here till here, I want you to write for Y direction. You write it once, then I will write. Then you can check what mistake you are doing. Okay, please be quick. Let us say all of us got this value. Don't work on this value again further. Let us say all of us got this value. Work for sigma Fy. Okay. Very good, very good. I'm sensing many of you, Amit, Anil, Ashish, Power. I think you are getting correct answers. Let me check now. Okay. Okay, sigma Fy. अब लेफ्ट हैंड साइड देखेंगे हम sigma Fy. Is he going to contribute in sigma Fy? No, he is purely in X. Is he going to contribute? No, he is purely in X. Yes, he is going to contribute. He is going to contribute. Look at the direction since Ry is having. Ry is upward. So I'll write Ry upward positive. P2A2 is in which direction? You see the component of P2A2, force component P2A2 in Y comes downward. Easily I'm writing minus. I'm writing minus over here. अच्छा कितना रहता वो, how much will that be equal to? ये देखिए, this is cos 60, that will be sin 60, so it is P2A2 sin 60. Believe me, I'm going really very slow, please try to follow. Okay, I don't go this much slow generally, it is paining me to go this much slow actually. Now this is equal to अब final section की बात करेंगे. Final section, look over here, V2 is having a component upward. V2 is having a component upward, and that component V2 upward will be equal to how much? V2 sin 60. So I can write over here m dot multiply to final section positive है इसीलिए V2 sin 60, V2 sin 60 minus initial velocity is completely in x-axis. It has zero component in y-axis. So therefore this value, luckily for you, this value is equal to 0. This value is equal to 0. This implies the value of Ry is equal to P2A2 sin 60 plus m dot into V2 sin 60. I'm hoping that most of you have got this value, got this equation. Exit of the pipe is not open to atmosphere. If it was open to atmosphere, P2 value would have been 0. I did not give you the value 0 over here. It is not open to atmosphere. Chaliye. Now you can say Ry is equal to how much? What is P2 over here? You can put in the values. 15,000. Area is 0.05 into root 3 by 2 plus m dot is equal to how much? M dot is equal to 1000 times 0.2. Velocity V2 is equal to 4 into root 3 by 2. Get me the value of Ry now. Ry. Most of you have given me the answer 1342. I'm taking 1342 newtons as answer. This is equal to 1.342 kilonewtons. 1.342 newtons. Now the question was asked to me regarding the net value of reaction or the net value of support force. So net value of support force has to be equal to root over of Rx square plus Ry square. Someone please use calculator. Get me the value of net value of force. $13.044 kilonewton. ठीक है, I take the answer as 13.044 kilonewton. Again, the value of Ry I got is positive. That means the direction sense I have chosen is perfect over here. Nothing wrong with the direction sense over here. This is regarding the concept of momentum flux equation. I hope you are following this thing. Acha, very good question. Bhushan Patil, really good question. Why are we not considering the weight of the fluid? Very, very good question. Okay, as a matter of fact, I thought of considering it initially. I thought of giving it in the question initially, but then I thought it would become slightly difficult for you. That is why what I did, I mentioned X and Y plane over here. X and Y plane का मतलब क्या है? Please try to imagine. देखिए, X and Y plane basically means the pipe is bending like this. The pipe is bending like this. If the pipe was like this, then the component of weight would come. Are you following? Then the component of weight would come. This is actually in horizontal plane. When I say X and Y plane, it is horizontal plane. In horizontal plane, the weight actually acts in which axis? Z axis. इसीलिए we have not taken this thing. Okay, but I really appreciate that question. Thank you, Ashish Pawar. Chaliye, now I'm going to speak to you. If you have questions, please ask. I'm really having less time actually, 10 minutes only, not more than that. Other faculty has to come in over here. Yash Patel, please speak.
Hello, good morning, sir.
Morning, sir.
Sir, actually, I understood all, but I am confused in this momentum flux in practically, like how.
Do you understand momentum first of all?
Yes, sir. Mass into velocity that is changing with respect to time.
No. Mass into velocity changing is not momentum.
That
Momentum
is
is
rate of change.
mass times velocity.
Yes, sir.
Mass times velocity is momentum.
Hmm.
Okay. Momentum flux basically is that momentum is crossing a section per unit time. Let us say there is some momentum over here. There is some momentum over here. Let us say some 3 kg meter per second is a momentum. That momentum is crossing a section per unit time.
Yes, sir.
It is crossing per unit time. In 1 second, 3 kg meter per second momentum is crossing. That is going to be now 3 kg per second square. That is going to be your momentum flux. Basically, momentum flux क्या है? Mass into velocity crossing per unit time.
Okay. Now got like combination mass into velocity per unit time. Like उनका change कितना हो रहा है एक point से दूसरे point तक.
नहीं. एक देखिए, एक दरवाजा है, मान लीजिए एक डोर है. एक डोर है. इस डोर से जो है 3 लोग जा रहे हैं 1 मीटर पर सेकंड की वेलोसिटी से.
जी सर.
ओके. तो एक सेकंड में कितना फ्लो हुआ, इसके कितना मोमेंटम?
3 का मतलब
3 kg मीटर पर सेकंड.
हाँ सर.
उसको मोमेंटम प्लस कहेंगे.
ओके सर.
ठीक है, थैंक यू.
यस सर, थैंक यू.
मोहम्मद जहांगीर अंसारी.
Good morning, sir.
मॉर्निंग सर, टेल मी.
Sir, I have a doubt on slide number 8F.
स्लाइड नंबर 8.
Yes, sir.
टेल मी.
How velocity VA equals to 0, sir?
See, if you are rotating something, the
Yes,
value
sir.
of velocity has to be equal to radius into omega, r into omega, right?
Yes, sir.
Now what is the radius of point A?
0.
So r into omega is 0, no?
Okay, sir. Sir, I think that it's open to small. At this point is open to atmosphere. That's why it is 0.
I showed over here closed container, closed. You see, whenever I am
Oh.
having closed है वो, इसीलिए. ठीक है ना?
Yes, sir.
Okay.
सर, और सर हमने क्वेश्चन भेजे थे आपको दो, उसका आपने आंसर नहीं दिया.
आप एक्चुअली देखिए, मेरे को कई क्वेश्चंस आ रहे हैं, मुमकिन नहीं है हर किसी का आंसर करना, लेकिन फिर भी आप एक बार रीमेसेज कर दीजिएगा. एक्चुअली इट्स नॉट
जी सर,
पॉसिबल.
3 दिन हो गया सर.
3 दिन हो गया, तो वही
Yes,
शायद
sir.
छूट गया. कई क्वेश्चंस आ रहे हैं, छूट जा रहे हैं कई क्वेश्चंस. मुमकिन नहीं है हर क्वेश्चन का आंसर
जी
करना.
जी
आप फिर से थोड़ा
जी
रिमाइंड कर
सर.
दीजिएगा. ठीक है. और
जी
बुरा मत मानिएगा अगर आंसर नहीं कर पा रहे हैं, क्योंकि एक ही
नहीं सर. Sir, I know you all are very busy.
ओके देन फाइन, लेट मी नो अगेन प्लीज.
Okay, sir. Thank you.
सौरभ कुमार ठाकुर, स्पीक.
हेलो सर.
हेलो, गुड मॉर्निंग.
हाँ, गुड मॉर्निंग सर. सर, ये फ्री वॉर्टेक्स मोशन में सर एक्सटर्नल टॉर्क लग नहीं रहा है, तो सर वो घूम कैसे रहा है?
फ्री वॉर्टेक्स मोशन में एक्सटर्नल टॉर्क लगने रहा है तो घूम कैसे रहा है? देखिए, जनरली फ्री वॉर्टेक्स मोशंस जो होते हैं वो किसी रैंकिन वॉर्टेक्स मोशन के नतीजे में होते हैं. मैक्सिमम टाइम ये कंडीशन होता है. ओके. यू आर गोइंग टू हैव सम पोर्शन एक्सपीरियंसिंग टॉर्क, सम पोर्शन नॉट एक्सपीरियंसिंग टॉर्क. ठीक है. फॉर एग्जांपल, I told you that when you are actually creating a vortex motion in a bucket of water.
Yes,
Hello,
sir.
are you able to listen?
Yes.
When you are creating a
Yes,
vortex
sir.
motion in a
Hello.
bucket of water, that time I told you it is approximately forced vortex. लेकिन strictly speaking that is also a Rankine vortex case only. आप हर पार्टिकल को टॉर्क नहीं दे पाते हो. कुछ फ्लूइड पार्टिकल्स को टॉर्क दे पाते हो, कुछ फ्लूइड पार्टिकल्स बिना किसी एक्सटर्नल टॉर्क के मूव करते हैं, क्योंकि उनको ये फ्लूइड पार्टिकल्स मूव करवाते हैं. ठीक है. So generally free vortex motion takes place whenever you are going to have some Rankine vortex. Apart from this, one more very good example of free vortex motion is, imagine you are having a sink. पानी भर दिया आप इस सिंक में, अचानक से एक छोटा सा होल क्रिएट कर दिए. अब यहाँ पे जो है बिना किसी टॉर्क के पानी स्वेल करता हुआ नीचे जाएगा. Excuse me, I'm getting some disturbance. Are you able to listen?
Yes, sir.
That kind of vortex motion is again going to be vortex motion, free vortex motion only. Okay, no?
Okay.
Okay.
सर, तो आप जब बोले कि फोर्स वॉर्टेक्स मोशन वाले पार्टिकल फ्री वाले को करवाएंगे सर, तो वो लोग तो अपने बाउंड्री में ही रिवॉल्व करेंगे.
अपने
अपने मतलब जैसे फोर्स का जो बाउंड्री है उस
जी
पे ही वो लोग रहेंगे, तो वो लोग फिर फ्री को कैसे रिवॉल्व करवाएंगे?
नहीं, मान लीजिए मान लीजिए यहाँ पे कि ये लास्ट पार्टिकल है यहाँ का, ये लास्ट
अच्छा,
पार्टिकल है यहाँ का, उसके बाद वाले पार्टिकल कुछ ना कुछ इन्फ्लुएंस तो करेगा,
यस।
उसी तरह से आगे चला जाएगा वो।
सर ये फ्री वॉर्टेक्स मोशन का जो आइसोबार होगा वो सेम होगा वो फोर्स की तरह?
नहीं, नहीं होगा, नहीं होगा। आइसोबार इज नॉट गोइंग टू बी सेम, इट इज गोइंग टू बी डिफरेंट। यू आर गोइंग टू गेट सम काइंड ऑफ हाइपरबोलिक इक्वेशंस। वो बहुत ही कॉम्प्लेक्स इक्वेशन की जरूरत नहीं है, लेकिन फिर भी आप डिराइव कर सकते हो उसको यूजिंग, आई हैव शोन यू ना इन दिस पर्टिकुलर स्लाइड, यूजिंग दिस पर्टिकुलर स्लाइड यू कैन डिराइव दैट इक्वेशन। क्या करेंगे आप यहाँ पे P1 और P2 को कैंसिल कर देंगे, V1 की जगह पे C/R1 लिखेंगे, V2 की जगह पे C/R2 लिखेंगे, देन यू कैन डिराइव दैट पर्टिकुलर इक्वेशन।
डेटम ले लेंगे। और सर ये जो प्रेशर रेडियस से वैरी कर रहा है, ये दोनों केस में वैरी करेगा वैसे?
किससे वेरी, क्या फिर से पूछिए?
प्रेशर जो
हाँ
रेडियस से वैरी कर रहा है
जी,
वो दोनों फ्री और फोर्स में सेम वैसे ही वैरी करेगा ना?
हाँ इक्वेशन तो बिल्कुल सेम रहेगा। ओके, इक्वेशन इक्वेशन जो है बिल्कुल सेम रहेगा। ओके, ओनली थिंग इज ओमेगा की वैल्यू फोर्स में कांस्टेंट रहेगी, फ्री में वेरी करेगी।
ओके।
ओमेगा की वैल्यू
तो
हर
ये जो आप
पार्टिकल फोर्स में कांस्टेंट रहेगी, फ्री में वेरी करेगी।
हम्म, और सर ये जो आप इक्वेशन ऑफ प्रेशर को मतलब ये फ्री और फोर्स के लिए डिराइव करने के लिए बोले ना
डिराइव
सर,
करना है।
वो बाउंड्री कंडीशन नहीं आप होमवर्क दिए ना इक्वेशन
अच्छा,
ऑफ प्रेशर के लिए?
मैं बोल रहा था कि इस इक्वेशन को डिराइव, इस इक्वेशन को इंटीग्रेट कीजिए, इंटीग्रेट करके ये इक्वेशंस प्रोड्यूस कीजिए बोल रहा हूँ।
सर तो बाउंड्री कंडीशन वही हो जाएगा ना, v
बाउंड्री
इक्वल्स
कंडीशन के अंदर लेट अस से एट पॉइंट 1 प्रेशर P1, R इज इक्वल टू R1, Z इज इक्वल टू Z1, एट पॉइंट 2 प्रेशर P2, R R2, Z Z2, ऐसे कर लो,
टू?
आपको आ जाएगा वहां से। ठीक है,
ओके
ट्राई कीजिए, अगर नहीं आया तो आप लेट मी नो, आई विल हेल्प यू आउट।
थैंक यू।
ठीक, थैंक यू सर। स्वरंगी मराठे, हेलो,
So good morning, sir.
मॉर्निंग मैम,
Hello. Hi, sir. I have doubt in this vortex motion only. Sir, you said that in this vortex motion doesn't apply around the center of the axis, right?
no, I did not say like that. I said vortex motion need not be about the centroidal axis. It
Okay.
can be about any axis. For example, if you are creating, let us see, if you are creating rotation about this particular axis,
Okay.
so then every radius has to be measured from here. You are not supposed to measure radius from centroidal axis.
Okay. But if it is acting in centroidal axis, then
Huh.
it can be called rotation also, na sir?
No, it is not called rotation. Rotation, what is rotation? If there is a particular fluid element, it is revolving around its own axis, that is called as rotation.
Okay.
Acha, you tell me one thing. This is, let us say, sun. This is Earth's orbit. Earth's orbit.
Hmm.
Okay. Earth is revolving around its own axis.
Yes.
That revolving around its own axis is creating rotational flow. Then Earth is rotating about sun. वो correct है? वो भी correct है ना?
Yeah. Yes, sir.
That is going to create vortex motion. तो vortex motion के लिए अपने axis से rotate करना जरूरी नहीं है. It has to rotate about some particular axis. Rotational flow के लिए about its own axis.
Then here centroidal axis will be its own axis only, no sir?
No, for every fluid particle, for this particular particle, tell me, is the central axis its own axis?
No, no.
हर एक किसी का अपना अपना individual axis रहेगा ना?
Acha, for like infinite particles are there, then infinite.
Individual axis will be there.
Okay. Okay, I thought just one axis, this
No, no, no.
centroidal axis for whole body.
No, no, no. Every particle, when we say rotation is basically, the rotational flow basically means a fluid element should rotate about its own axis. Element can be infinitely small. Every element is there. Infinitely small. ठीक है?
Okay, sir. Thank you, sir.
Thank you, man. Shivani. Shivani, this will be the last doubt for today's class. Let me know. Shivani?
Why didn't you consider weight, sir? I didn't get that.
Acha, in that question, why didn't I consider weight?
Yes, sir.
One second, that question here. Okay, this, madam, this is in which plane XY plane. This is in XY plane. Okay. First of all, you have to get an idea of XYZ plane, XYZ axis. Ye X axis hai. This axis, which is, are you able to see my hand over here?
Yes, sir.
This is X axis, let us say. This axis is Y axis. Tell me, where is weight acting? Vertical, na? That is Z axis. That is Z. So right now, this is in horizontal plane. That means it is something like this. Horizontal plane. Ab aise rehta, if that bend was something like this, then it is X and Z axis.
Okay.
Right now, it is in X and
Got it.
Y axis. Na? That's why.
Yes,
Okay.
sir.
Thank
Thank
you.
you, sir.
Thank you, man. Afzal Unnisa.
Hello, sir.
Hello.
Sir, I have doubt in 15F.
15F. Tell me. Yes, tell me.
I have a doubt in 15F, sir.
Yeah, this is 15F slide, no?
Yes, sir.
This is, yeah, tell me, what is the route?
Sir, I didn't get that second point of control volume.
No, this is not, you're talking
Accelerate.
about this particular slide, is it?
Yes, sir.
Achha, this is 16F.
It should not be accelerating that point.
See, whenever you are having a particular system accelerating, that particular frame of reference is called as non-inertial frame of reference. In the case of non-inertial frame of reference, Newton's law of motion is not valid. Okay. So
Okay.
in non-inertial frame of reference, you can refer to your 11th class physics, non-inertial frame of reference, Newton's laws of motion, Newton's laws of motion are not valid, are invalid. If these become invalid, automatically the equation of momentum also will become invalid, because the equation of momentum is actually from Newton's second law of motion. Is it fine?
Okay, sir.
Okay, thank you.
Sir,
Yes, ma'am, tell me.
sir, but weight acts vertically downwards, no, sir? Whatever that.
This is x-axis, this is y-axis, this is z-axis. Vertically down is z-axis in this case. xy, xy, this is z. This is z. Okay. This is x, this is y, this is z. Weight acts in z-axis. We are talking about xy plane over here right now. Fine.